Okay, we'll continue our discussion on voltage regulation. So, voltage regulation we already discussed in the last class. Percentage voltage regulation is E naught minus V by V. If you already brought this material, you can write on the same notes. Okay. So E naught minus V into 100 here. Okay. This is percentage voltage regulation here, and we already know this. The relation between generated EMF and terminal voltage for a synchronous generator is E equal to V plus IA into ZS, where ZS stands for synchronous impedance. ZS stands for synchronous impedance. ZS is combination of RA plus J, XA plus XL. Okay, XA plus XA is nothing but armature reactance, and XL is nothing but leakage reactance. Okay, now here under short circuit condition, under SC short circuit condition, what happens here? This terminal voltage will be 0, and then E equal to IA will be under IA, V will be 0 and IA will be ISC. IA current will be short circuit current. Okay, IA current will be short circuit current here. Then equation will be changed to E equal to ISC into ZS. So here ISC is equal to E by ZS. So always we want the short circuit current to be less. For this, what we want here? We want this synchronous impedance to be more here. Okay, we want the synchronous impedance to be more here, and and there is one more equation. We can also say that we already written this E equal to V plus IA into ZS, or else E minus V equal to IA into ZS. So if ZS increases, then E minus V also be increases here. So where this E minus V concept is there here, it is in their percentage voltage regulation, and if E minus V has to be increases here, which term has to be increasing here? Percentage voltage regulation has to be more. So we always in that I am concluding this here, in synchronous generator, percentage voltage regulation should be more. Should be more. That is at least 35 to 40 or 50 percentage. 40 or 50 percentage. Because to limit the short circuit current, percentage voltage regulation has to be more. I hope it's clear. Okay. Okay. Percentage regulation has to be more. So if it is more here, then synchronous impedance will be more, and if synchronous impedance is more, then short circuit current. So even in any abnormal conditions, if the machine comes under the short circuit case here, the short circuit current has to be less, so that the minimum damage can be happen into the machine, and that's why we always recommend it to be the high percentage voltage regulation here. High percentage voltage regulation here. Okay. So yes, sir. So what is voltage regulation here? Change in voltage from no load to the full load here. Okay. So voltage regulation. So we already discussed that it is percentage voltage regulation is nothing but E naught minus V by V into 100. Okay, E naught minus V into 100 here. Okay. Next here, this this voltage regulation can be measured. Okay. For this, in order to check this voltage regulation, what we require here? E naught is where? E naught is no load voltage. E naught is no load voltage. V is terminal voltage. E naught is no load voltage. V is terminal voltage here. Okay. So here, when the machine is, how can you able to get this E naught? E naught can be obtained. Okay, under open circuit condition, and terminal voltage under load condition. Okay, when it is connected under the load condition here. So when we can operate the machine under no load condition we can able to get this E naught, and when we operate the machine under the load condition, then we can able to get the terminal voltage. Similar to this, when fan is off, so what are the voltage that is available here? That is no load voltage. When the fan is on under load condition, we can able to connect this, and we at the terminal side, the voltage will be terminal voltage or output side voltage here. Okay, this is what the difference here. So for this, we need to conduct the test directly. So if I want to test the what is the no load voltage and full load voltage across the fan, okay, then I have to operate fan manually. Okay, that test I can say that direct loading test. The test is called as direct loading test. So what is direct loading test? Simply connecting the machine and applying the no load voltage and short circuit voltage here, okay, or full load voltage here, and taking the difference here, E naught minus V by V. Then we can able to get the percentage voltage regulation. It's like conducting exams directly, okay, and giving the results here. Whereas, so here you already know this in power plants like Srisalmar, Nagarnu Sagar, okay, where the size of the power plants are very high here. The range is approximately 900 kilowatts. Okay, approximately the rating is very high here. Okay, so in order to for this heavy rating machines here, I cannot apply the loads. You know, just to test the machine, I cannot apply the load here. Okay, why I cannot apply the load just to test the machine? Because heavy power loss takes place here. Okay, power is we need to utilize the power in a proper manner, and where just to test the machine, I cannot apply the full load conditions or maximum load conditions. Okay, so power loss, there will be huge power loss if I want to test this voltage regulation, and if I want to apply the full load condition. For that case here, instead of applying the full load full power or full load condition here, we are also going with the another methods here. Okay, where we can get the voltage regulation. We can able to get the voltage regulation from the another methods here. That is EMF method. Okay, EMF method. So these are all the methods are indirect methods here. These are all the methods are indirect methods. What is that? First one is EMF method, electromagnetic okay, EMF method, or you can also say that synchronous impedance method. EMF method or synchronous impedance method. I'll try to write fast here. Second one is MMF, magnetic force method, or the Rother's ampere turns. That's ampere turns method. Third one is ZPF method, or what is ZPF method? Zero power factor. Zero power factor method. There is also one more name here. It is also called as Portier triangle method. Portier triangle method. Okay, Portier triangle method. Last one is ASA method. That is American Standard Association method. ASA method, American Standard Association method here. So here I told you that the second unit is one of the easiest units, and if you want to pass this EM2, so what is the other alternative here? So the other alternative is you must learn these 4 methods. You can get directly 10 marks for both theory as well as for numerical. In the 4th unit, there are heavy chances of getting these questions directly. Okay, even these will be there in EM2 lab also. Okay, these will be there in EM2 lab also. Okay, so we'll try to discuss one by one in detail here. Just I'll be quick. Okay. Okay, I'm proceeding. So EMF method, MMF method, ZPF method, and ASA method. Okay, so let's try to discuss one by one. So try to concentrate more so that it will be easy. Okay, so we discussed about the different methods here. Okay, so this is direct loading method. So how direct loading method is there? First, before that, I'll try to show you that how this what is the circuits and what are the parameters here. So this is star connected stator, star connected stator. So understand clearly here. Okay, star connected stator, armature winding. Okay, where the armature winding is placed here? In the stator. Okay, and the field, normally we say this is stator and the inside one is rotor. This is rotor, okay, that is stator. In stator is armature winding is accommodator, and the rotor field winding is accommodator. Now here the stator is connected with which supply? Okay, now I'm discussing about generator. So generator which converts mechanical energy into electrical energy. So here there is stator as well as rotor. Rotor is nothing but field winding. Field winding has to be excited with which supply? This is field winding. Whatever I am representing here, this F1, F2 are field winding. This field winding is always excited with which supply? It is excited with DC supply. It's excited with DC supply here. Okay, and coming to this state, okay, when field winding is excited with DC supply and it is placed near to that, it is when it is rotating here. Okay, EMF is generated here. That EMF can be measured in terms of VL and IL here. What are these VL and IL here? This is the output terminal voltages here at the no load or full load conditions. If I connect here, that will be no. If I don't connect, that will be no load conditions. If I connect, that will be loaded condition here. And this is a three-phase load here. What is this TPS is full form? TPS stands for triple pole single through. That means by closing switch at a time, I can able to close 3 poles here, 3 phases. So this is triple pole single through. So what is this PM? Prime mover. So when this prime mover is connected to the rotor, that means indirectly I am making the rotor to rotate. Okay, by using which case here? Prime mover. Okay, I am making the rotor to rotate by using the prime mover here. So and prime mover is and the rotor is connected with DC supply. When it is excited here, it starts rotating as per the Faraday's law. We can able to generate the EMF. Now what we are most bothered about here? We want to find out percentage voltage regulation, that is E0 minus V by V here. So E0 can be obtained by connecting the open circuit conditions here. By connecting open circuit conditions. And coming to the V, when I am closing this TPS switch, I can able to take the readings here. So when I take both readings, is it sufficient to measure this percentage voltage regulation? Am I correct or wrong? Yes? So we can able to get the sufficient readings here, that is E0 minus V by V here. This is directly applying the load here. Just now I told you this. So for a huge machines, for high loss rating machines here, so power loss is very, very important drawback here. So just to test the machine, okay, I cannot apply this 1.1 megawatt or okay, so high rating power applications here. Okay, for that reason here we are going with the other testing methods here. So this is what's specified. For high capacity alternators here, full load cannot be simulated directly here. Okay, and this direct loading test is suitable only for which motors, which machines here? Small rating machines here. So let's try to discuss this first method here, synchronous impedance method. The remaining 4 methods are indirect methods here, and which can able to find voltage regulation. But we will not apply full load here. We will try to take some characteristics and okay, from that we can able to determine the percentage voltage regulations here. To our college, there are so many ways here, like Nasapur or Sangareddy or okay, Medak. Even this percentage voltage regulation in indirect also, they have approached different methods here. They have strategies, and we'll try to discuss that each one advantage as well as drawback, and which one is near to the actual value here. Okay, so synchronous impedance method. So the test is okay. The circuit diagram is same as that of the previous case here. I hope there is no need to discuss again here. So same star connected stator and field winding with the excited DC supply, and here this is always field winding supply. I can also call it as excitation directly. Okay, field winding supply I can also call it as excitation, and this is field current here. Okay, and this is VOC, open circuit voltage here, and this is short circuit current here. In the last classes we have discussed about the few characteristics here. Open circuit characteristics here. Open circuit characteristics are drawn between E0 versus IF. Instead of VOC, I can also say that it is E0. Okay, and second one is short circuit characteristics. Short circuit curves are drawn between ISC versus IF. Okay, open circuit characteristics are this is open circuit characteristics OCC between E0 versus IF. And coming to the second one here, short circuit characteristics are drawn between ISC versus IF. We already discussed in the last class, and just I'm revising the same here. So what we'll do here, so synchronous impedance method is also called as EMF method. Okay, so what we require here, we require armature resistance. Okay, and what we do here will as we see in the diagram, as we see in the diagram here, we'll try what we'll do here, we'll apply the DC supply, and we'll make the machine to rotate its okay, we'll connect the prime mover, and once the voltage starts generating here, we'll try to take the no load, we'll try to take the no OCC characteristics here. How can I able to plot the OCC here? For different values of field currents, for different values of field currents here, we'll try to note down the no load voltage, and we can able to draw the characteristics here for different values of field currents. Okay, we can able to, there is a rheostat is there here. By varying the rheostat, we can able to change field current here. We can change the voltage, okay, as well as we can able to change the field current here. By different values of field current, we can able to change the we can able to get the different values of voltage, and same we can able to draw here that characteristics are we can call it as OCC characteristics. Okay, and coming to the short circuit characteristics here, how short circuit characteristics are obtained here, by the name itself is short circuit here. So that here I am closing this TPST switch. For a short circuit characteristics, I am closing the TPST switch, that is short circuit is done. So now here whatever the voltage that is there, now the voltage is 0. As the short circuit is done here, voltage is 0. And what is the current that is flowing here? That is maximum current here, and that's why it is called as short circuit current here. How this short circuit current is measured here? Again, by varying for different values of IF, we will try to note down the different values of ISC here. So we can able to draw the characteristics here. It is obviously the characteristics will be linear here. These two characteristics are important for this method. I hope it's clear. Whatever I explained in the previous classes, I repeat it again here. So from this experiment, we'll try to measure OCC characteristics as well as what is the other one? Short circuit characteristics. We have measured the OCC characteristics as well as short circuit characteristics. Next. So how I am going to measure here? So let me try to write here. So here graph. So first what I will try to do here, I will try to draw the open circuit characteristics. Okay, try to draw simultaneously here. Okay, is it visible or not? Yes. Okay, try to draw open circuit characteristics quickly. Okay, so here we can able to apply the open circuit characteristics here. Up to some extent the characteristics are linear. After that, saturation will be affected here. Okay, this is drawn between E0 versus IF. Second thing is, once open circuit characteristics are drawn here, what I will try to do here, again I will try to draw short circuit characteristics. So instead of taking in the same line, I will try to take in the separate y-axis. But starting point it is from here on. Okay, in a single graph I am trying to represent two characteristics here. Okay, in a single graph I am trying to represent, the starting point will not be here, the starting point will start from here itself, even from the short circuit characteristics, and the y-axis will remain, x-axis will remain same here, that is IF only. Okay, so the y-axis, so again for different values of field current, try to measure ISC, that is ISC for different values of field current. This is E0 versus IF here. This is how we will try to measure this open circuit characteristics as well as short circuit characteristics here. The scale has to be same for on the x-axis, and we have to represent. And after this, how to obtain this synchronous impedance method. Okay, so I hope it's clear. Okay, once it is done, so we can draw a dotted straight line anywhere. We can draw a, okay, we are supposed to draw a dotted straight line. Okay, on the okay, with this and we have to measure that point as IF here. Okay, Measure that point as IF here. To this common point of IF here, measure the corresponding values of E naughts. To this common point of IF, measure the corresponding points of E naughts, and simultaneously measure the corresponding points of ISC. Measure the corresponding points of E naught as well as measure the corresponding points of ISC. Okay. So let it be some 20 amps or let it be some 220 volts. What are the values that? Okay, I'm just taking a random straight line or dotted line here. So on which projects onto the IF here for the same IF here. Okay, take the corresponding values of node on. Okay, extrapolate the corresponding values of E naught as well as ISC here. So what will you do with this here? So that's now let's try to write here synchronous impedance. Now we are trying to find synchronous impedance here. The synchronous impedance formula is nothing but E naught, open circuit voltage by short circuit currents. I'm directly in short. Open circuit voltage by short circuit current for same field currents. IF or fixed value. For a fixed IF current here. For a fixed value of IF current here. For a fixed value of IF current, open circuit voltage by short circuit currents. Okay. For a fixed value of IF here. Okay, that is E naught by ISC. How we are obtaining this E naught and IF dotted straight line. Okay. And next E naught value. Okay. Take the E naught value as well as what is E naught here? Open circuit voltage. What is ISC here? Short circuit current. For the corresponding to the field current, let that for 15 amps of field current, this is the open circuit voltage and 20 volts, 20 amps is the corresponding short circuit current here. If I take different values, then again these values will change. Okay, I can also take this point also. Okay, to this the corresponding open circuit value will change here. This is E naught 1 and this corresponding field current will also be changed here. This is ISC 1 here. Okay, it's up to us. Okay, open circuit voltage by short circuit current here. Okay, what are the value that we get single, that is not the accurate value, exact one here. Okay, this is graphical method so that you can get different values here. Okay, so once it is done here, this coming to the competitive exam bits here, this ZS can be calculated in several ways here. Okay, this is normal method. We can take, this is user defined. So user will be given an option where I can select, where I need to select this characteristics. Either I can start from the starting point or ending points. Okay, so instead of this, I can also instead of this, what I can do here, try to draw fast. Okay, so this is ISC and this is short circuit condition here. Now here there are several ways to represent this, calculate this ZS here. One is ZS saturated, one is ZS, this is second method, ZS saturated. So what is saturated here? Saturation condition. That is, saturation word is relevant to which parameter? Magnetic flux. Yes or no? If the field current is increased to up to 100%, then the flux will reach to 100%. If the field current increases beyond its rated value, flux will not increase. That concept we call it as saturation. If there is no field current, if there is no saturation, the characteristics will be like this. The characteristics will be like this for the EMF generation. Okay, the characteristics will be like this. Okay, as there is a saturation, as there is a saturation, okay, you can see this. As there is a saturation, the characteristics will be slightly bending here. Okay, the characteristics are slightly bending. Okay, or else you can say that the characteristics are. Now what is the heading here? ZS saturated. That means in order to find out the ZS saturated, I need to locate these points. I need to locate this point at the saturation region. Okay, in order to get the saturated ZS saturated here, I need to locate the this dotted straight line. In which place? In the saturation region. Okay, if I want to inform something to the third year students, then I need to go to third year class. Okay, if I want to inform the same to the second year, then I need to go to the second year class. I cannot go in the wrong place and convey the same information, whatever they require. Okay, similarly For ZS saturated, the dotted line has to be represented in where? Saturation region, and the formula will remain same. So here, okay, sorry, that means what we'll try to do here, okay, I'll just conclude this. So here, for how will it select here, we will try to take this rated voltage here. We'll try to take the rated voltage, that E naught value, we'll try to take the rated voltage. To this rated voltage, what are the corresponding points are there here? Okay, the corresponding points and the short circuits, that will be measured here, and corresponding field current will be measured. I will try to take the rated voltage. I will try to take the rated voltage, and I will try to extrapolate onto the OCC characteristics. From that point here, then extrapolate onto the YF, as well as same point has to be extrapolated into the, it should be here. It should be intersecting point is, and extrapolate into ISC. So I can conclude that what is the formula here? ZS saturated is equal to E naught by ISC at IF at rated voltage. IF value, how I am selecting this IF here? I am selecting IF value in such that it should be equal to the rated voltage. Where is the position of the rated voltage? It is similar, it is in near to the open circuit voltage, or it is in the saturation region. That's why I can able to get the ZS saturated. So they may ask you these slightly different questions. Only thing is where you are representing this. So ZS saturated is nothing but E naught versus IFE at IF equal to V naught V saturated. V saturated. And there is one more formula, one more method is, that is ZS unsaturated. ZS unsaturated. So ZS unsaturated is nothing but, what is this? ZS unsaturated is nothing but, I'll try to write on the formula directly here. So we will try to take the rated current here. I'll try to take the reference as what? Rated currents. I'll try to take the rated current as reference, and from that I'm trying to extrapolate into, yeah, I'll try to take different color here, that's it only. So I'll try to take the rated current here, that is I rated, and to this take the corresponding field current, and for the corresponding field current, note down the corresponding E naught here. So ZS unsaturated equal to E naught by ISC under IF. What is the value? How I am taking IF here? IF at rated current. IF equal to rated current. This rated current is obviously existing at unsaturated region here. Okay, that's why it is whatever the ZS I am getting here. That is ZS unsaturated. This is ZS unsaturated. Okay, this is how we are going to calculate ZS value, saturated, unsaturated, or if nothing is given in the question, then you can select any value. Okay, if they specify ZS saturated, you have to consider this rated voltage as a reference here. If current is if they say that ZS unsaturated, then I can need to select as rated current as a reference here. If they don't specify anything here, take any random value, draw the corresponding E naught by, okay, draw the corresponding voltage by current here. Okay, just quickly draw this. Okay. Okay, so this is how we have to calculate ZS. Okay, so once ZS is calculated, now ultimately finally what I need to find here, I need to find out voltage regulation. In order to find out the voltage regulation, what I want here, I need to get E naught here. Okay, so what I'm trying to do here, after finding ZS, okay, so let me try to use this. Okay, there are some graphical phasor diagrams are there, so it will be easy. So this is what we discussed so far. Okay, whatever the diagram that we draw, is it relevant to this or not? Okay, so we can able to plot this open circuit voltage and short circuit current, and from this we can able to measure the synchronous impedance. Once synchronous impedance is measured, we have this ZS equal to V open circuit voltage by short circuit current here. Next, so this is how for a single phase, the corresponding values will be like this. This is open circuit voltage and this is V. Okay, so how this regulation is calculated here, we have the formula here. Synchronous impedance equal to RA square plus XS square. What is XS? XS is nothing but synchronous reactance. RA, what is RA here? Armature resistance. Can I able to calculate this armature resistance? By using multimeter, can I able to calculate or not? Yes, I can able to calculate the RA by using the multimeter. Okay, so out of this, just now I calculated ZS and I also calculated RA. Okay, by using the multimeter. Can I able to calculate XS? What is the formula of XS here? XS equal to under root of ZS square minus RA square. So this is how I can able to calculate. Okay, ZS square minus RA square. Next, after finding this XS, I can able to draw the phasor diagram. This is the corresponding formula. E naught equal to V phase cos phi plus IA RA whole square plus V phase sin phi plus or minus IA XS whole square. Just write down this formula. We will now justify how you got this formula here. Okay, why I am requiring this XS here? Because XS is there in the formula. Okay, as XS is there in the formula, that's why I am using this. I am trying to find out XS. In order to find out XS, I need ZS. I am using this ZS by using the synchronous impedance method. That is from the graphical method. Okay, and already what is V here? V is nothing but terminal voltage or rated voltage. Now all the machines in any question also they will specify that 230 volts or 415 volts. That's a rated voltage. That's indirectly terminal voltage. Terminal voltage is already given. Okay, they will specify in the question. But only thing is from terminal voltage I need to find out no load voltage. Okay, from terminal voltage I need to find out no load voltage. Is that clear or not? Okay, so these are the corresponding phasor diagram of unity power factor load. Here, what is the relation? We already discussed in the last classes here. So E naught, what is the formula here? E equal to V phase plus IARA plus E equal to V plus IARA plus IA XS. So that I am trying to represent here for different power factors. Okay, what is the phasor diagram here? Okay, so the same concept will be utilized here. So instead of this IARA, how can I replace here? I can replace it with IA into ZS. So this instead of IARA, IAXS. So I guess there is no need to repeat again here. The same phasor diagram what we discussed in the just 2 days ago here. So for a unity power factor, what is phase angle here? 0. That's why I am drawing IA in the same phase here. Okay, and IARA has to be drawn in parallel with IA phasor, and IAXS has to be drawn in perpendicular with respect to IA phasor. The resultant of this IARA, IAXS is IAZS here. So what I want here, V phase, IARA, IAXS will be E phase. Okay. Now here I don't know this E phase. How can I able to calculate this E phase? Is it in the shape of which triangle? Right angle triangle. Am I correct or wrong? For a right angle triangle, so A square plus B square equal to C square here. So that is, so this length, let's assume that x square x, this length is some y, and what do you want here? This is z, I don't know here. Okay, so z equal to under root of x square plus y square. So that is V phase. Okay, it's already represented here. So yeah, E phase equal to OA plus AB. What is OA here? V phase. AB is nothing but IARA. So that is BC square. So that means E phase equal to V phase plus IARA whole square plus IAXS. If I try to rewrite the equation, the formula will be E phase equal to under root of V phase plus IARA whole square plus IAXS whole square. This is for unity power factor. Okay, we have written the generalized equation. Now I am going to show for different power factors what the formula. Okay, we can adjust the same equation So shall I proceed with the inductive load here? So most of the cases will go with the only inductive loads here, 90%. So same. Say now instead of drawing previously in the previous slide, what we have seen here, we have considered the V phase as reference from the x-axis. Now what I will do in the next case here, I will try to consider V phase as this, or else I will try to consider the I phase as IA as a reference. I can consider anyone as a reference. Yes or no? I can, as per my requirement, I can consider any point as reference here. So here, for my better understanding, I am considering IA as a reference. Okay. For my better understanding, I am IA as a reference, and as it is lagging power factor. What is phi here? Phi equal to some 30 degrees to 40 degrees, which is lagging with respect to V here, or else voltage leads current here. So that with respect to this voltage is V phase is drawn here. Next, what is the equation just now we written here? E phase equal to V plus IA RA plus IA into XS. Where should I draw IA RA phasor? From the end of this V phase, I have to draw IA RA phasor. So what I'm doing, in similar to this, in parallel to IA, I'm drawing IA RA phasor. Next, how should I represent IA XS here? In perpendicular to IA XS phasor. IA phasor, I have to draw IA XS phasor. The resultant of these two will be IA into ZS. The resultant of these two will be IA into ZF, and from this the phasor sum of these two will be, it is E phase. Okay, the same phasor sum of these two will be E phase here. Now what I need to find now? I need to find out E phase. Ultimately, I don't know E phase. Okay, listen clearly. Just you can note down later also. Okay. Now here, I know phi. Okay. I know V phase. V phase is already known to me. Known parameters are V phase, phi. Okay. And IA. Okay. From this, if I consider this as a triangle. Okay. If this is a phase angle and this is a hypotenuse. Okay. Okay. This value is hypotenuse. Can I able to find out this value? What is this value here? Cos theta equal to adjacent side by hypotenuse. Adjacent equal to hypotenuse into cos theta. So what is the value here? Can I write this as V phase into cos phi? So if I want to write here cos phi equal to this value here, this is unknown, this x value by V phase. So if I want to rewrite this x equal to V phase into cos phi, that's what I am writing here, V phase into cos phi. Similarly, I want to find out this value also. This is sin theta. What is sin theta here? Sin phi equal to, now this value is y. I am writing it as y here. Y by, what is this value here? Hypotenuse is V phase. Y equal to V phase into sin phi. So this value I am writing it as sin phi. Okay. So I am trying to find out same thing here. Again, this is also in the right angle triangle. Now the phasor sum of these two will be this E phase here. What is the phasor sum of these two here? So it is V phase cos phi plus IARA whole square. Okay. E phase whole square equal to, I am writing here V phase cos phi plus IARA whole square plus, what is it, the y-axis that is in the vertical side here, it is V phase sin phi plus what is this, IA into XS whole square. So if I rewrite here, then the E phase equal to under root of V phase cos phi plus IARA whole square plus V phase sin phi IA into XS whole square. Is this the formula what we discussed just now? Okay, this is the formula for lagging load. Instead of writing every time here, just we are concluding here. Okay, even if you don't understand this concept also, that will not be any major effect onto the, okay, you need not to draw this phasor diagram in the numericals or for a small okay, for a 5 marks questions here. Just if you directly writing this formula also will be sufficient. Only thing is remembering this formula. And what I did here, how we got this formula? Okay, we got this complete derivation. This is for which load here? Lagging load. Similarly, I'm just skipping this here. Similarly, I can, there is also the phasor diagram. Okay, if I go with the leading load also, instead of this plus, I'll get minus here. The equation will be V phase sin phi plus minus plus or minus IA into XS whole square. Okay, V phase sin phi plus or minus Ia into Xs whole square. So okay, this is the voltage regulation formula for synchronous generator by using which method? EMF, by using EMF method, or else synchronous impedance method. This is the corresponding diagram for leading power factor. I guess only thing is a bit okay. The graph is not given here. The formula is correct one here. We have to take minus here. For leading it is minus. For lagging it is plus here. You can write down this for plus or minus. For plus for lagging here, lagging loads. Minus is for leading load here. Okay. What are the advantages here of this here? Advantage of this method. The advantage is nothing but I'm applying direct loading here. This advantage is common to any method here. So I'm not applying any direct loading here, and still yet I'm able to find out the percentage voltage regulation. So how can I able to get the analysis here? Whether whatever the calculated value, if it is equivalent to the nearer to the actual value, then only we can able to confirm that it's good method, or this method is useful. So yeah, here the percentage voltage regulation measured by using this method is more than the percentage voltage regulation actual. Try to remember this here. For EMF method, what we are getting here, the percentage voltage regulation measured will be more than the percentage voltage regulation actual. This is a competitive exam bit here. Okay, so we always get more than the actual value of voltage regulation method, and that's why this method is called as pessimistic method. This is the drawback what I am saying here. This is pessimistic method. This is the pessimistic method. Okay, this is the pessimistic. Only advantage is nothing but we will not apply direct loading here, and we can able to estimate the percentage voltage regulation. What is the drawback here? So we are getting the more than the actual value of percentage voltage regulation. That's why it is called as pessimistic method. So how we are getting this pessimistic method? Okay, the voltage regulation is more than the actual here. So the explanation is, we can just have a small explanation. We know that synchronous reactance is a combination of leakage reactance and armature reactance, XL plus XA. Now in EMF method, in EMF method, entire armature reactance is considered as leakage reactance. Entire armature reactance is considered as leakage reactance. So that what happens here, XS will be now equal to only XL. As I am not considering this XA separately, I am assuming that entire armature reactance is also equal to XA here. I am getting more than the actual value. Okay, and that's why this method is pessimistic method. Not okay. We are not exactly recommended here. Okay, this is all about the synchronous impedance method.